So we're at about 2,300 degrees for the surface temperature.
For Matthew Fiore, the heat is on. This little bead is made of what's called a rare earth oxide. It's a high-temperature material.
High-temperature materials, very loosely speaking, are materials that are like rocks. Nothing much happens to them until you heat them up.
With support from the National Science Foundation, chemist Alexandra Navrotsky and a team at the University of California, Davis have built this instrument to study the structure and stability of rare earth oxides when they reach their melting point. That's when chemical reactions can start to take place.
All the interesting things that happen in terms of their thermodynamic properties, in terms of their changing from one structure to another, occur at temperatures at white heat and above, let's say 1,500 degrees centigrade.
Rare earth oxides are a key component in many electronics. Cell phones, batteries, lights, medical scan machines, and many more devices all contain these relatively poorly understood elements.
We have erbium, lutetium, thulium, ytterbium, neodymium, we have yttria, we have, oh geez, I should be able to name all of them.
They begin their study of the rare earths by making them into little beads.
The problem is at high temperature, everything reacts with everything. How do you overcome that problem? You try to make a sample such that it's not in contact with anything other than the inner atmosphere. How do you do that? You levitate a sample.
The technique is called drop and catch calorimetry. They levitate a bead, zap it with a laser to melt it, and then drop it.
And so what happens is that the bead is heated up here and it falls, and then we just, like that.
As the bead solidifies, sensors behind those copper plates measure heat flow and a property called heat of fusion, how much energy it takes to melt the material.
If you want to calculate how many different materials interact with each other, you do this by a series of theoretical calculations, and these properties of the melting have to go into that.
Navrotsky says insights gleaned from this work could have applications for nuclear waste storage. Rare earths are a byproduct of nuclear fission. Also, the aerospace industry, in the form of new heat-resistant materials for spacecraft, and also improved coatings for aircraft engines to keep them from overheating.
We've built it and we are still improving it little by little. Eventually, perhaps it will get commercialized, but right now it's a prototype, and as far as I know, we're the only ones that have anything like it.
Matthew Fiore helped develop this instrument as an undergraduate. For him, breaking new scientific ground has been a revelation.
Honestly, when I first realized it, I just kind of sat there for a minute just being like, this is magic. Because through the development and work of others, all those generations, you kind of feel like, I don't know, I guess I get kind of philosophical on it. You actually feel like you're a part of a grander movement, something that's really important and bigger than yourself.
Alex Navrotsky can appreciate his enthusiasm. She's been a chemist for more than 50 years, a leading one for much of that, a pioneer for sure, but an unassuming one.
Basically, I just, went my own way and did the things I wanted to do and perhaps surprised myself, look where I am. Only in retrospect do you realize that you were a pioneer. It's all in a day's work.
Going to extremes, probing the properties of high-temperature materials, unmasking the mysteries of rare earth oxides. For Science Nation, I'm Miles O'Brien.